work. Okay, so it's told me that the recording's happening. And so without any further ado, thank you very much for coming along to this this episode of the Wing Seminars. It's a little bit earlier than normal, normally at the end of the month, but EGU is coming up, and that's at the last Thursday of the month this month. So we're jumped forward by a week, and we've also moved from the East Asian time zone we were in last time over into something more like the west coast of the US, and it's my pleasure to introduce Xiaojing Du. Sorry, you can say your own name correctly in a second. Who's going to talk to us about her postdoc work, and she volunteered for this. So if other people out there would like to give talks and would like to volunteer, then they are also welcome to. So maybe I can pass over to you, Xiaojing.
Okay, thank you, Chris. Thanks for the introduction. And it's my honor to be here at the PMIP Wing seminar to share my work when I was at a postdoc at Brown University about the zonal mode over the tropical Indian Ocean during Heinrich Stadial 1. Yeah, and before I talk about my work, I would like to acknowledge all my collaborators on this work, and their contribution really make it this work possible. And also, I would like to acknowledge the Voss Postdoc Fellowship at Brown University and also the support from NASA. Okay. Yeah, so since the topic of today's seminar is climate change in the tropics, so I would like to spend a little bit of time to talk about the tropical atmosphere circulation and how it influences the tropical rainfall before I introduce my work on the tropical Indian Ocean and during the Heinrich Stadial 1. The distribution and the intensity of tropical rainfall is largely controlled by Walker circulation, which is the east-west circulation, and also the intertropical convergence zone. The Walker circulation is an east-west circulation over the equator, and we can see there's a strong ascending branch over the Indo-Pacific whirlpool, which is also the largest tropical deep convection zone in the world. And the photo on the left shows the convective cloud towers from the Western tropical Pacific. They form when the warm, moist air near the Earth's surface rises rapidly, cools down, and condenses into visible water droplets. And it can produce thunderstorms, lightning, and also heavy precipitation. And the descending branch of Walker circulation occurs over the eastern tropical Pacific and the western Indian Ocean. And the Walker circulation over the tropical Pacific is associated with El Nino Sun oscillation, and the Walker circulation over the tropical Indian Ocean is associated with the Indian Ocean dipole. Both of them are very important internal climate variability modes, and is associated with extreme events in both sides of the tropical Pacific and the tropical Indian Ocean. And another very important component of the tropical atmosphere circulation is the intertropical convergence zone, or ITCZ. The map here shows the annual mean precipitation from 1979 to present. And the precipitation data is from the Global Precipitation Climatology Project dataset, which is based on both satellite datasets and the rain gauge data. And light color means lower precipitation, and the darker color means higher precipitation. So we can see there is a dark blue band near the equator, which indicates a tropical rain belt. And this tropical rain belt is ITCZ, the intertropical convergence zone. And the formation of ITCZ is due to the convergence of the trade wind from both north and southern hemisphere. the northeasterly trade winds from the northern hemisphere, and the southeasterly trade winds from the southern hemisphere meet near the equator and force the air up into the atmosphere. And also the strong sun and the warm water at the equator also heat the air and make them more buoyant. The ITCZ also forms helicells, which are responsible for transporting energy out of the deep tropics into the subtropics, and also the heat transport across the equator. To be more specific, the lower branch of the helicell, which is indicated by the gray arrows, can bring warm and moist air masses toward the ITCZ from both northern and southern hemisphere, and they converge and rise and diverge as they getting cooler and drier aloft. And because of the moist static energy in the upper branch of the helicell is greater than that near the surface. So the helicell can transport energy away from the tropics to the actual tropical region. And the asymmetries in the energy export out of the tropics to the northern and southern hemisphere lead to an energy flux across the equator. For example, the ITCZ is located near the equator, but it's in the northern hemisphere. So the energy export into the southern hemisphere is greater than that in the northern hemisphere. So that leads to a southward cross equatorial energy flux. And the cross equatorial energy flux is very important to keep the inter-hemisphere energy balance. And the position of ITCZ can shift both northward and southward. On seasonal time scales, the ITCZ follow the sun because the sun hits the air and make it more buoyant. And ITCZ moved northward in the northern hemisphere summer and moved southward in the northern hemisphere winter. And on longer time scales, the position of ITCZ is correlated with a temperature contrast between the northern and southern hemisphere. ITCZ tended to move away from a cooler hemisphere, or in other words, it tends to move toward a warmer hemisphere, so that the heat transport across equator is directed from the warmer hemisphere to the cooler hemisphere. And again, this process is important to keep the energy balance between the northern and southern hemisphere. And moreover, the northward and southward shift of ITCZ could also impact the strength of the east-west Walker circulation by changing the strength of the trade winds. And the interplay of this east-west and the east-west Walker circulation and the north-south shift of ITCZ plays a critical role in controlling the variation in tropical rainfall. In addition, the tropical rainfall can also be influenced by processes outside of the tropics. For example, the differential interhemispheric heating or differential interhemisphere cooling in high latitudes can influence the tropical rainfall by shifting the position of ITCZ, because they can change the temperature contrast between the northern and southern hemisphere. And this process can lead to a tropical polar teleconnection. And the work I'm presenting today is about the tropical response to North Atlantic cooling during the Heinrich Stadial 1. So how the tropical region will respond to this abrupt North Atlantic cooling event. And this is also associated with the polar tropical teleconnection. The Heinrich Stadial 1 is a rapid North Atlantic cooling event, and also it's also the largest and the most abrupt climate change event since the last ice age. And this event is associated with massive glacial meltwater from the Laurentide ice sheets into the North Atlantic. And the large piles of fresh water into the North Atlantic can reduce the salinity and increase the buoyancy of the seawater in the North Atlantic. And that will weaken the deep water formation in the North Atlantic, and consequently leading to reduced Atlantic meridional overturning circulation. We know the Atlantic meridional overturning circulation, or AMOC, is responsible for the heat transport from the tropics to the Northern Hemisphere. So the slowdown or the shutdown of AMOC during the Heinrich Stadial one will lead to abrupt North Atlantic cooling. And I was wondering, how does the tropical hydrological cycle respond to the Heinrich Stadial one, to the North Atlantic cooling during Heinrich Stadial one? The Heinrich Stadial one occurred during the last deglaciation, when the Earth's climate underwent large shifts in a couple of aspects. For example, change in the greenhouse gas concentrations, atmospheric greenhouse gas concentrations, and also change in sea level associated with change in ice sheet extent, and also seasonal insolation change due to orbital forcing. And also abrupt North Atlantic cooling during the Heinrich Stadial one because of the freshwater input from the North Atlantic. Yeah, and this event provided an opportunity to investigate the tropical response to North Atlantic cooling and how the different boundary conditions can modulate the relationship between the tropical and the teleconnection between the tropical region and the polar region. So in this work, I bring together paleoclimate proxy vectors and the climate model simulation to reconstruct the spatial pattern of hydroclimate change in tropics, and also using model simulation to investigate the underlying dynamics. As to the climate model, I use iTrace, which is the first set of SW-enabled transient simulation in Earth's model. Is based on ICESM 1.3, and iTrace includes 4 single forcing simulation corresponding to climate shifts during since the last ice age, including change in ice sheets, extent and sea level, greenhouse gas concentration, orbital-driven insolation, and the meltwater flux. Yeah, and the change of this forcing are also shown in this figure here. And the single forcing analysis enable us to investigate the influence of different forcings. And previous study on the tropical response to North Atlantic cooling has long been focusing on the north-south dipole structure of precipitation due to the meridional shift of ITCZ. As we discussed in the introduction, the position of ITCZ is correlated with temperature contrast between the northern and southern hemisphere. ITCZ tend to shift away from the cooler hemisphere. So when the northern hemisphere getting cooler during the Heinrich Stadial one, the ITCZ will shift southward, and the southward shift of the tropical rain belt will lead to a drier condition north of the equator and wetter condition south of the equator. And this pattern is indeed observed from precipitation records from like the Western Africa and South America. However, in the meltwater flux simulation in iTrace, we found the North Atlantic cooling during Heinrich Stadial one triggered a unique zonal dipole structure, east-west dipole structure over the tropical Indian Ocean, in contrast to the north-south dipole structure in other basins like the Atlantic and Pacific Ocean during Heinrich Stadial one, and also the north-south dipole structure across the tropics during under dryers. And the east-west dipole structure during Heinrich Stadial 1 is not only observed from the precipitation, but also from the sea surface temperature and thermocline depths from both proxy records and model simulation. For example, we compiled the precipitation-sensitive proxies like sea level, pollen, digital flux, leaf wax, and also Speedy Awesome, and we found a widespread drought in the tropical East Africa and a wetter condition in the central and eastern Indian Ocean, including the south and the eastern maritime continent. And the simulated sea surface temperature anomalies also show a zonal dipole over the tropical Indian Ocean with enhanced warming in the Eastern Indian Ocean, including the Bay of Bengal, and moderate cooling or less warm in the Western Indian Ocean, and particularly in the Arabian Sea, which is also evident in SST proxy data. Moreover, we found both proxy records and model simulation indicate a deeper thermocline in the Eastern Indian Ocean and shallower thermocline over the Western Indian Ocean. And the precipitation, sea surface temperature, and thermocline depth change indicate there is a stronger worker circulation over the tropical Indian Ocean during this period. When the worker circulation over tropical Indian Ocean getting stronger, the increased convection over the Eastern Indian Ocean will lead to increased precipitation, and the westerly anomalies will reduce upwelling of Sumatra and Java, and that will lead to warmer sea surface temperature and deeper thermocline in this region. And on the other side of the basin, the drier condition and the cooler sea surface temperature will occur. So the change in the precipitation, sea surface temperature, and thermocline depths all indicate a stronger worker circulation over the tropical Indian Ocean during Heinrich Stadial 1, and that contributed to the east-west dipole structure in this region. So to be more specific, the dipole arises because of the interaction between the North Atlantic heat transport, the ITCZ, and Indian Ocean worker circulation. When the North Atlantic is getting cooler, the southward shift of the ITCZ during Heinrich Stadial 1 will strengthen the heavy sail and trade winds in the northern hemisphere, and that will weaken the cross-equatorial southeasterly trade winds in the tropical Indian Ocean, and that will lead an anomalous westerly across the equatorial Indian Ocean, and the westerly anomaly will suppress the summer upwelling of Sumatra and Java, and that will contributing to the deeper thermocline and warmer sea surface temperature in the Eastern Indian Ocean, which will further strengthen the worker circulation across the tropical Indian Ocean via the positive Bjorknes feedback. And the strengthened worker circulation is responsible for the Indian Ocean zonal dipole, featured by wetter and warmer condition and the deeper thermocline in the Eastern Indian Ocean, and the opposite response in the Western Indian Ocean. And this zonal precipitation dipole superimposed on a north-south dipole structure related to the southward shift of ITCZ, and that led to the precipitation pattern we see from the tropical Indian Ocean. And another question is why the east-west dipole structure is a unique feature in Indian Ocean, not in Pacific and Atlantic Ocean, and not in younger dryers. And we propose that the glacial boundary condition, especially the lower sea level and the exposure of continental shelves like Sundan and Sahel shelves and the northwest Australia shelf will change the tropical Indian Ocean mean state. Previous studies suggest that the exposure of the Sundan and Sahel shelf will establish a weak worker circulation background condition across Indian Ocean. And that condition opposes the zonal dipole over the tropical Indian Ocean during Heinrich Stadial 1 caused by the meltwater flux, and therefore can amplify the magnitude of the zonal dipole anomalies in Indian Ocean during Heinrich Stadial 1. And moreover, the glacial Indian Ocean mean state will lead to a shallower thermocline and a vigorous upwelling in the East Indian Ocean, which favors a strong air-sea interactions. And that leads to an increase in sea surface temperature variability over the tropical Indian Ocean. And the westerly anomalies along the equatorial Indian Ocean during Heinrich Stadial 1 will promote a warm phase-like Indian Ocean equatorial mode. So the increased Indian Ocean SIT variability will activate the Indian Ocean equatorial mode. And the westerly anomalies across the tropical Indian Ocean would lead to a warm phase-like Indian Ocean equatorial mode across the tropical Indian Ocean. And that will also contribute to the Indian Ocean zonal dipole. But of course, the relationship between the Indian Ocean equatorial mode and the millennial scale zonal dipole we observe from proxy and model simulation needs further investigated using both proxy records and model simulation. So what's the implication for the future climate? We think so we know the Arctic sea ice is shrinking under global warming, as indicated by the map here. The Arctic sea ice extent in the 2020s showing the map, and also the yellow contour indicate the median extent for the Arctic sea ice extents between 1918 and 2010. So the Arctic sea ice has been retreated by above 10% per decade since the availability of the satellite data. And IPCC report also suggests a higher certainty that the consequent freshwater input would weaken the Atlantic meridional overturning circulation and cause part of the Atlantic. On the other hand, the previous study also indicate the global warming would increase the sea surface temperature variability over the tropical Indian Ocean, and that will lead a similar mean state to the glacial condition. And the combination of the Arctic sea ice melt and change in the tropical Indian Ocean mean state under the global warming could lead to an east-west dipole over the tropical Indian Ocean and increase the possibility of extreme events on both sides of the basin. So here are the main conclusions from this work. I probably don't have time to go through this, but thank you for your attention, and I'll be happy to answer any questions, or you can also contact me via email or follow me on Twitter to interact more. Yeah. Thank you.
Thank you very much. That was a very nice talk. So we've got time for maybe one or two questions, and I'm going to kick off with the first of those. So stick your hand up if you've got other questions. And I was going to say, sort of in your simulation, have you looked at whether there are changes in the variability in the simulation? And okay, and were there?
Yeah, we look at the sea surface temperature variability in our simulation, and we do see the increase interannual scale. There are increased sea surface temperature variability during the glacial condition, like during LGM and also during Heinrich Stadial 1. Yeah, so that is consistent with the hypothesis. But the internal variability can be associated with the initial condition of the model. So probably in the future, it will be helpful if we can have, like an ensemble of the simulation to change the initial condition and keep the boundary condition the same to see whether there's constant results in the interannual sea surface temperature variability.
Okay. Wonderful. And so, John, you put your hand up, and I wonder if that's for a question or.
Yes, it's for a question.
So, but I'm going to start by saying, just before you do your question, Xiaojing, if I can get you to stop sharing your screen.
Oh, sure.
And then maybe we can start moving on to your talk itself, John. But so ask your question first.
Sure. Xiaojing, thanks for the talk. It was nice. I think in one of your slides, you showed the contrast between the Heinrich Stadial and the Younger Dryas response over the Indian Ocean, and they were different. So why is that?
Yeah, so that's a very good question. So that's one of the reasons why we think the glacial boundary condition matters for the zonal dipole, because during the Heinrich Stadial one, because of the glacial condition and the lower sea level, the shelf of the Sundance Sahel shelves were exposed. But during the Younger Dryas, the sea level is higher. So I think the change in the land sea configuration matters for the zonal depth. Yeah.
Thank you.
Thank you.
Wonderful. So if we can now move on to your talk.
Okay.
So
I'm getting saying I cannot share screen.
Yeah. So currently, and sharing option. I'm going to switch you to that. Xiaojing, you're currently sharing your desktop.
Oh, really?
Although not the. So if I switch that. So it might be that you can share your screen now, John. I've fiddled with a switch.
Okay. Let's see.
So if you can have a go.
Somehow I can't find the.
How's that? Is that right?
I think I'm still sharing my screen, right?
Yeah, I can see yours. I don't know what other people can see. I've got a view option of who to choose.
I can't find the. I don't know. Maybe I can quit and re-enter.
I think I've stopped sharing.
Oh, okay.
I've stopped sharing, and so can you try sharing yours again, John? Because I've stopped yours sharing too, as well, unfortunately.
How's that?
Yeah, so I can see the PowerPoint, but not in sort of presentation mode yet, though.
Got it.
Great, that's got it.
Okay, shall I begin?
Yes, please do.
Alrighty. Thanks for the opportunity. This is work done with Alyssa Atwood, Dan Vimont, Paul Nicknish, Will Roberts, Clay Table, and Tony Broccoli. I think Tony Broccoli is in the audience. So this is about the annual cycle of the cold tongue. And in 2015, Michael Erb, who was then a student of Tony Broccoli's, published this, which I thought was a really remarkable paper on the seasonality of the cold tongue in the Pacific. And what they showed was that under various phases of precession, the seasonal cycle of the cold tongue changed drastically in phase and amplitude. So in this work, which is published in late last year, we went about to figure out why. And the answer we came up with is that turns out that the Pacific cold tongue actually has two annual cycles, one which is driven from tilt, and this is one that's known, and the other one which actually is driven from orbital eccentricity, and this one's new. And because the two annual cycles have slightly different periods, they actually interfere with each other, so that's the reason why they get you get such a remarkable change in the precession as in the cold tongue seasonality with precession. So let me start by giving a couple of preliminaries. So I define the tilt effect as being the annual forcing from Earth's axial tilt. There's a year that's defined by this. So from equinox to equinox, and it's called the tropical year, 365.24220 days, and this is how we define our calendar. There is another year that comes from distance effect, which is the variation in the Earth-Sun distance with eccentricity. There is a quite called a nominalistic year, which is from perihelion, and it's slightly longer than the tropical year, about 25 minutes longer in the present day. Currently, the eccentricity ranges from 0 to 0.06. Currently, it's at 0.0167. In other words, perihelion is about 1.67% shorter than the mean Earth-Sun distance. Now, so perihelion today is close to winter solstice, but because the year behind perihelion is a little bit longer than the tropical year, if you wait over a period of time, the position of perihelion relative to solstices will shift. So it will shift to the counterclockwise and so on. So I'm going to define the position of perihelion relative to solstices by the longitude of perihelion, which is the angle shown in red minus 180 degrees. So for example, today's position of perihelion is about 102 degrees, right? So on to the Pacific cold tongue. So I think most of you know of this because of the El Nino Southern Oscillation, but it does also have an annual cycle, which on the outset can be quite surprising because the sun crosses the equator twice a year. So you would naively expect a semi-annual cycle, not an annual cycle, but it actually does have an annual cycle. And the annual cycle is shown at the bottom. So this is a half molar, month of the year in the y-axis, longitude on the x-axis, showing the climatological annual cycle. The cold season is in September, just after Northern Hemisphere summer, and the warm season is in March, just after Boreal winter. By the way, so if you look at the variance of the cold tongue about in today's climate, about half comes from ENSO, half comes from the annual cycle. All right. So why is there an annual cycle in the cold tongue? So this work has been the theory of this has been figured out in the 1990s by this is Todd Mitchell and Mark Wong's 1992, and then Xiaoping Xie, Ping Chen, amongst others, worked out the theory of it. The key feature of why there's an annual cycle is the southeasterly trades, which blows across the equator all times of the year because the ITCZ is biased to the north. And in fact, the strength of southeasterly trades determines the strength of the cold tongue, in that when the trades are stronger, you get more mixing and you have upwelling along the coastline, so you get colder conditions and vice versa. So looking at October, when the ITC is well north, you have strong southeasterly trades and the cold tongue is cold. In the opposite season, in April, the ITC is close to the equator, but not in the southern hemisphere, but in the north. The southeast trades are weak and the cold tongue is weak as well. All right. So in a nutshell, the prevailing theory argues these two key factors for the annual cycle of the cold tongue. The one being the interhemispheric thermal contrast that drives the variation in the southeasterly trades. And so this is attributed to the tilt effect. And the second is that the ITCZ is biased to the north. So this determines the phasing of the cold tongue annual cycle. So by this argument, were the ITCZ be shifted to the south, the phasing of the cold tongue will be flipped 180 degrees. So what I would say is that the theory was worked out in the 1990s, and since then we thought that, I think it was then thought that this was figured out. And so subsequently there has been very little work on the cold tongue, the seasonal cycle. Okay, so coming on to the paper that motivated the study. So this is a paper by Michael Erb and Tony Berkeley. So what they did was to run the GFDA model with a large but realistic eccentricity. So they took an EO of 0.0493, which I think is the maximum over the last 600,000 years. They changed the timing of perihelion, but they did not change the tilt effect. And this is what they get for the seasonal cycle of the cold tongue. So starting from perihelion at winter solstice, which is close to present day, you see the annual cycle. So cold in September, warm in March and April. But then as they change the position of perihelion, say now to vernal equinox, you can start to see the annual cycle phasing and amplitude change. So this is now at vernal equinox. Now this is perihelion at summer solstice, and then at autumnal equinox. So you can really see the phasing flips over, and the amplitude actually changes as well. So its amplitude is strongest in for 90 and 100 degrees longitude perihelion, and is weakest at 0 degrees. So this is remarkable because this should, according to the prevailing theory, this should not happen. Because in none of these simulations would the tilt changed. The tilt is still the same at 23 point whatever degrees. So by the prevailing theory, this change of annual cycle shouldn't happen at all. Okay, so we showed that this change in the phase and amplitude is robust across different models. So after the paper was published in 2015, I was working with Frank Lamy on a project using the EC Earth model. And which actually turned out to have a similar orbital parameters. So I took a quick look at their seasonal cycle, and it turned out to be similar to what they found in GFDL. So I got a little bit more excited. Then we contacted Clay Table, who had a similar run in ICSM1, and lo and behold, the same thing happens. Then we contacted Will Roberts, who had CM3 model, and asked him to do the runs again, and lo and behold, the same thing happens there. This appears to be robust. Okay, so in trying to figure this out, so I'm not that smart, so I just try to think about doing it as a brute force method by simply running CSM 1.2 spanning the orbital parameters in eccentricity. So I had runs going from 0.01, 0.02, 0.04, should be 0.01 rather, not 0.1, and also equals 0, and spanning the longitude of perihelion. So it's a lot of runs. Luckily, I was on sabbatical at the time. What made this also possible was that you could run it in relatively low resolution, and also you didn't need to run it that long because the seasonal cycle equilibrates fairly quickly. Okay, so here you go. So this is the results from the simulations. I'm going to use a cold tongue index, which is the average of sea surface temperatures over this boxed region. And then here's the results for the equals 0.04. So what I'm showing here on the y-axis is the months of the year, and then on the x-axis is the seasonal cycle at various longitudes of perihelion. So for example, at zero longitude of perihelion, if I wanted to know the annual cycle of the cold tongue, I'll just follow the dashed line going up. So for 0 degrees, the amplitude is quite small. So you'll notice two features of this result, which is one, you get a progressive phase shift. Secondly, you get a change in the amplitude, so that you get smallest amplitudes near 0 longitude of perihelion and the longest amplitudes near 108 degrees. So when I looked at this, I thought, well, this kind of looks like an interference effect. So I constructed destructive interference of two sine waves. So what we did was to just fit the results to a simple model of three cosines. The one cosine being the tilt effect annual cycle, the second being represented distance effect annual cycle. And the difference between the first two is that they basically have the same period, but because the distance effect annual cycle is a little bit longer, you get a linear shift in the phase, which is represented there. And then for good measure, we also introduce a semi-annual cycle to it. All right, so once we do so you get 6 parameters, 3 amplitudes, 3 phases. We did the fit to the data, and the fit works out very well. Then you can break it up into its various components. And basically this is the answer, that there's almost equal contributions from the tilt and distance effect annual cycles. The semi-annual cycle is small. So what this is saying is that the cold tongue annual cycle is actually 2 annual cycles, and it's actually a combination of the tilt and the distance effects. All right. So if you look at the same analysis but using the runs with smaller eccentricities, we find that the amplitude basically is linear with eccentricity. And in fact, then if you compare it with the amplitude of the tilt effect annual cycles, they're comparable at roughly when E equals 0.05. So basically at the largest eccentricities possible, the two annual cycles have roughly the same amplitudes. Today's eccentricity is fairly small, but even at today's small eccentricity, the amplitude of the distance effect annual cycle is about a third of the total effect. So it's not negligible. Right? So there you go. So the question is, so how is the distance effect cold tongue cycle generated? So this is the answer we came up to. There's two parts to it. The first one is that the distance effect actually induces a large-scale circulation, which I call the zonal monsoon, that shifts the Walker circulation, and that shift in the Walker circulation in turn forces the annual cycle through ENSO-like dynamics. All right, so let me go through each one in turn. So what we found was that the annual cycle, how the annual cycle is expressed in the tropical atmosphere is actually through an east-west shift in the Walker circulation. So during perihelion, the Walker uplift region shifts towards the Africa, and vice versa for the opposite season. So this is kind of like the ITC migrating north and south, but for the total effect. And the reason why the Walker circulation shifts is because you need a contrast, a thermal contrast to give you a pressure gradient that drives circulations. Now, during perihelion, the sun it increases flux everywhere, but the contrast is given by the boundary conditions between what I call the continental hemisphere, which is more land than ocean, and the marine hemisphere, which is mostly ocean. So, for example, during perihelion, when the Earth is close to the sun, you warm up the continental hemisphere more than the marine hemisphere. So, as a result, you shift the Walker circulation towards the continental hemisphere and vice versa. The way we did this in the paper is actually through atmospheric energy flux method, which is kind of what Xiaojing mentioned for the ITCZ, but in the north-south sense. We actually did this for the east-west sense. So I don't really have time to go into this, but it's in the paper if you're interested. Okay, so that's the first part, that the distance effect annual cycle basically shifts the Walker circulation east and west because of this contrast between the continental and marine hemispheres. Okay, the second part is, okay, so why does this drive a cold tongue annual cycle? And the answer we get is that, so the Pacific has this ocean atmosphere dynamics that gives rise to the ENSO. And it actually works in a similar way, except that it's actually a forced annual cycle driven by the changes in the trade winds from the Walker circulation shift. So for example, during aphelion, when the Walker circulation is shifted towards the Pacific, your easterlies are weak. So then that drives a wind forcing on the tropical ocean atmosphere system, leading to a warmer cold tongue a couple of months later, and vice versa. So during perihelion, you get stronger easterlies and then colder cold tongue. So it's basically just an annual cycle forcing going like that. All right. Okay, so on to implications. So what are the implications of the study? The first implication is that the cold tongue annual cycle is not a solved problem. I think there's still things to be worked out there. In terms of paleoclimate, so this is a model result. So the question is, can we actually see this in the real world? So in terms of amplitudes, I think you can do this. So there are core records of the Pacific in the Holocene, I think, that shows reduced amplitudes, and that's consistent with what we find. But the more interesting thing is one of phasing. But then this is harder because you need to affix a monthly calendar to the paleo record. And I've spoken to various people, and I think this no one's been able to do this thus far. On the corollary side, so a lot of paleo studies of the tropical Pacific focus on the El Nino submodulation dynamics. But our results would suggest that you actually would pay more attention to the seasonal cycle of the cold tongue. And very lastly, so this is a result for the cold tongue, but you can ask the question, does the distance effect annual cycle is it relevant for other regional climates on Earth? And in fact, my preliminary investigation of this suggests that there are regions that where the distant effect annual cycle actually is important as well. Anyway, so that's my conclusion, and I'll just end there.
Thank you very much for that. That was a really nice explanation of what's going on. I'm going to open the floor if there's any questions. And so maybe people can, yeah, I can see Bridget would like to ask a question. So maybe you can ask that.
Hi, I really enjoyed that talk. It's fascinating. I need to read the paper as well, but I was particularly really interested because, so I worked on the equatorial Pacific, but on older records, and we see eccentricity cycles in what appears to be warming and cooling of the cold tongue. And this is in the middle Miocene, so about 15 million years ago. So I've been looking for an explanation for these eccentricity cycles that are out of phase with the high latitude cycles. And so this is really exciting to me.
Well, thank you for that. So the boundary conditions then, I assume, are a little bit different. So I would wonder if the dynamics of the Pacific are the same as today's. And so the result we have is about the I guess it's on precession cycles, which is a lot shorter than I guess million year cycles. But the amplitude of this effect depends on how large eccentricity is. So obviously, if you have a zero eccentricity, you do not have a distance effect annual cycle, and vice versa. So yeah, is that record published?
No, because we were trying to find a kind of an explanation for these cycles. So so it's definitely something to think, because like you say, the boundary conditions will be different, and the gateway, the Central American Seaway, will be open.
Right.
But I think it's really, really amazing that you can see these cycles in the modern. I think potentially we're seeing these in the paleo record.
Great, wonderful, thank you. I'd love to see it come out.
Yeah, I'll get in touch.
Brilliant. Thank you very much. I don't know if anybody else has questions. I haven't seen any raised hands. Oh, Chiang, maybe you can go on and ask your question.
Okay. Hi, John. Thanks for the great talk.
Okay.
You mentioned that the continent and the marine Earth, the thermal contrast between the two can trigger the monsoonal circulation, and also light dynamics is also important. I'm wondering whether you can reproduce the result using, say, slab ocean, and does that tell us regarding the importance of the dynamics?
So in the paper, how we established that result was we actually reran those simulations in slab ocean mode, so without the tropical ocean atmospheric dynamics, and then we took those winds and then forced the KNZBAC model with it. So basically what that does is to establish that it's the winds. The winds are driven by the ocean atmosphere contrast, and then the winds in turn kick off the dynamics that gives you a forced annual cycle of the cold tongue. Yeah, so it's in the paper.
So in your slab ocean results, you should see a much muted response, right, than the fully coupled one.
It's muted in the sense that the cold tongue obviously doesn't respond, or responds very little. Yeah, but the winds are there.
Okay.
Yeah.
Thank you.
I can see that Frank had his hand up next.
Hey, hello. Can you understand me?
Yes, I can hear you.
Hey, Joe, that's the microphone. Thank you, John. This is Frank from Amsterdam. Very interesting talk. And as soon as you raise the eccentricity on 100 kiloyear cycle, the paleo people start to wake up as well. So my question actually is that when there's such a strong effect of the eccentricity, would you think like there would be like a tropical origin of the ice ages somehow, you know, because it's so strong in the model? So do you think like there's a potential relationship?
Yeah, that's an interesting one. And in fact, Tony and I have been talking about this a little bit. The short answer is in principle, yes. In practice, we have no idea how this is going to work. I think I'm not going to answer your question, but one of the large implications, so what we learned from the study is that we should treat the distance effect as an annual cycle in its own right. So in other words, what we're saying is this, is that, you know, we consider eccentricity in paleoclimate, but the way we consider it is as a modulation of the total effect annual cycle.
Exactly.
So we say that, you know, for example, the Green Sahara, you know, greenhouse Sahara is there is because the summers are warmer. But I think what we are saying is that you really shouldn't think of it that way. We should really think, you should really separate the two annual cycles. The Earth actually experiences two annual cycles, not just one.
Exactly. Yeah.
So I think if you ask the question in that sense, maybe you'll come up with a slightly different way of interpreting things, as we did for the Khotan, for example. So I'm not answering your question, but I'm saying maybe there's a different way of thinking. Tony, I'm wondering if you have any comments about that.
No, I think you put it very well. I had my hand up mainly in response to the question about the slab ocean, because I was going to point out that in the Erb et al. Paper, we did run the same experiments with the slab version of the GFDL model, and we don't see the changes in the annual cycle. We don't see those phase shifts. So there is a direct comparison between two models in which the atmospheric component is identical, and the only thing that's different, and the forcing is identical. The only thing that's different is the slab ocean replacing the fully coupled model.
Interesting. And so I guess I'm conscious that we're approaching, well, dinner time for me here in London, but I think I'm happy to wrap it up here before 6 o'clock. But if there's going to be another one of these in a month's time, but I don't quite know what it is yet. It'll probably be involving some discussion, possibly from Massa and I, about what is going to be happening in PMIP and doing some organizational stuff, as well as hopefully some actual science. But that leaves me to thank both of the speakers today, both Xiaojing and John, for really nice talks. And there's obviously things that might want to, like, contact them, send them emails and get some collaboration going, and hopefully there's some discussion going on otherwise. So thank you very much, everybody.
Great. Thank you, Chris. Thanks for organizing.
Thank you for everybody being here. Bye.
Thank you.